Today we are going to discuss the module 4 of integrated circuits and applications. So this module 4 describes the DC analysis of dual input balanced output differential amplifier configuration. In the last module, we discussed the various configurations of differential amplifier. Out of that, we are going to discuss the first type of differential amplifier configuration, that is dual input balanced output configuration. And here we are going to describe the DC analysis of dual input balanced output differential amplifier configuration. So in the last module, we discussed that two common emitter amplifier configurations which are identical to each other are coupled via a common emitter resistor RE towards the negative power supply. So then you can construct the differential amplifier. So two identical CE amplifiers are used. That identical means that the two collector resistors of two transistors are equal. So RC1 is equal to RC2 is equal to RC. RC1 is equal to RC2 is equal to RC. Similarly, here you can see RC1 is equal to RC2 is equal to RC. Similarly, because it is identical to each other, the two input resistors are also equal. So Rin1 is equal to Rin2 is equal to Rin. And now because we are going to evaluate the DC analysis, that is nothing but the operating point characteristics or Q set characteristics, which is nothing but the collector current and output voltage, that is VCEQ, that is collector to emitter voltage and the collector current IC. So these are nothing but the output characteristics or quiescent point characteristics or operating point characteristics. Now here we are going to determine the ICQ and VCQ of Q1 as well as Q2. Because the two transistors are identical to each other, the DC analysis or the quiescent point is same for both Q1 and Q2. So calculating one equivalent to the other. Now, in order to calculate the ICQ, first of all, you have to write the base to emitter loop equation, KVL expression for base to emitter loop of Q1. So here you can see, because it is DC analysis, all the AC sources must be kept at zero potential. So here we have two inputs because dual input. So two inputs are Vin1 and Vin2. Because it is DC analysis, DC inputs are present and AC input signals are kept at zero potential. So it is nullified. So Vin1 is equal to 0 volts and Vin2 is equal to 0 volts. So both are grounded. Now here you can see. So that is because both are 0 and now you are going to write the KVL for base to emitter loop of Q1 transistor. So it will be Rin1 into IB, that is base current of Q1, plus VBE plus IE into, see here you can see that the amount of current flowing through emitter resistance is 2IE, because IE is the amount of current flowing through emitter terminal of Q1 is IE and Q2 is also IE. So total current will be 2IE flowing through the emitter resistor RE. So the same circuit here again we represented. So we have written the KVL for base to emitter loop of Q1 and represented as equation 1. So Rin1 into IB plus VBE plus capital RE into 2IE. Here you can see capital RE into 2IE minus VE is equal to 0. So this is equation 1. Now here you have an additional term IB, because we are going to focus only on calculation of quiescent current. So this IC1 is approximately equal to IE because base current is almost all negligible. because V in 1 is equal to 0 volts. So IB is equal to IE by beta DC. So IC is equal to IE is equal to beta IB. So where beta suffix DC represents the beta suffix DC represents the current gain of CE amplifier under DC analysis. Therefore, upon replacing IB as IE by beta, you can represent IE as VEE minus VBE by 2RE plus RN by beta DC. Because here I have taken IE as common. If I take IE as common, it will be RN by beta plus 2RE. So that will come under the denominator, and you can take the minus VE and VBE towards the right side. Then it will be VE minus VBE by 2RE plus RN by beta DC. So this is equation 2. So now where VBE is nothing but the cut-in voltage of the transistor Q1, which is the amount of input voltage required for the transistor to turn into the on state. So it is equal to 0.6 volts for silicon transistor and 0.2 volts for germanium transistor. So it is VE minus VBE divided by 2RE plus RN by beta DC. So this is our quiescent current, which is also equal to approximately equal to IE. So that's why ICQ is represented as IE by VE minus VBE by 2RE, because this RN by beta DC, because beta is higher value, 2RE will be far greater than this magnitude. So we have neglected this this Rn by beta, and neglecting Rn by beta, we can get IE as VE minus VB by 2RE. This is quiescent current. Now we are going to determine the quiescent voltage, that is VCE. Here from the circuit again you can see VCE is nothing but the voltage at the collector terminal minus voltage at the emitter terminal. Here the voltage at collector terminal can be obtained as a drop VCC minus the drop at RC. So VCC minus IC RC is nothing but voltage at the collector terminal. Similarly, you can observe that the voltage at emitter terminal is equal to minus VBE, because VBE can be represented as VB minus VE, but VB is grounded because we are evaluating the DC analysis. AC signal is 0. So VB will be 0 and VE is directly equal to minus VBE. So VB minus VE is equal to VBE. Because VB is 0, VE will be directly equal to minus VBE. So directly, what I told you, VC is equal to VC minus VE, where VC is the voltage at collector terminal, which is VCC minus ICRC, minus what is VE? VE is the voltage at the emitter terminal, that is equal to minus VBE, because VBE is VB minus VE, because VB is 0. VE will be directly equal to minus VBE. So finally we obtain the quiescent voltage VCEQ as VCC plus minus of minus VBE, that is VBE minus ICRC. So now we calculated the operating point characteristics as the quiescent current, which is VE minus VBE by 2RE, 2RE plus Rn by beta, but we neglected Rn by beta compared to 2RE. And VCEQ is VCE, it is equal to VCC plus VBE minus ICRC. So by changing the operating point characteristics, we can stabilize the output of the transistor. And here one more point that we have to remember is that the DC analysis, that is the calculation of ICQ and VCQ, is same for all the 4 configurations, because we are using almost all the same biasing arrangement, and we are setting the AC input signals to 0. So DC analysis remains same, and it is equal to ICQ is equal to VE minus VBE by 2RE plus Rn by beta, and VCQ is equal to VCC plus VBE minus ICRC. So with this we can wind up the module 4 of integrated circuits and applications. I think the students learned the DC analysis, that is calculation of VCQ and ICQ for all the 4 configurations, that is dual input balanced output, dual input unbalanced, single input balanced output, and a single input unbalanced output. Because the calculation part, like DC analysis, will remain same for all the 4 configurations. Thank you for listening.